Vâng, và vậy vâng chào Sorry, okay, so this time we will discuss our homework. The office time is Wednesday and Thursday and Thursday. Okay. This page is the notice page. You have to know. If you copy the homework, you will be punishment. And the due date is October 31. October 31 at 9 o'clock. And don't submit this. Okay. And please upload the homework to the IP on this IP. And with this user ID and password. And the most important is you have to use this file name.
不用高兴没关系，远一点都可以看。
You have to use this file name. If you change your version, you can modify the version number from V1 to V2. And this page is the Python version that we recommend you to use. Here the question will be 5, and I will introduce the first homework question, the camera calibration, and I'm Kirby. And the most important thing is do not fix your image text. If you fix the image text, you will face some error. And by the way, you have to create the UI. This is the example. You can use the example as your UI, or you can create your own UI. And the first question is camera calibration. And it will make with 5 small questions. And you can see the equation on the right side. The RT is extrinsic matrix, the K is intrinsic matrix, and the D is distortion matrix. The transformation is below on the right image. Okay. So the first one is corner detection. We give you the 15 image, and you can use the below function to detect the corner on the chessboard for each image. The first function is cv2.find chessboard corner, and the input is gray image and width and height. The parameter of the function is on the right side. You can see it, and the return value is RET. If return value RET is equal to 1, it means it finds a corner. Otherwise, it cannot find the corners. And the other output is corners. The corners means corners point on image coordinates. And the next function is cv2.corner subpixel.
This the image will keep.
If you use this function, you can see the image below. Each corner has the single color. You can see it. I can play the video.
Image like this one, right? 15.
Yeah. Has its own with the different. So the second function is used to increase the corner accuracy. And the input is gray image and corner.
subpixel actually.
But yeah, subpixel. And the win size, zero zone, and criteria is the parameter that we recommend you to use from the OpenCV. If you want to change it, it's okay. And in the UI, you press button, it will show this image. This is what we ask for. And the below parameter, the win size is the range of the search area near the corner point. And the zero zone is the window size prevent from focusing on edge of image. These two parameters is used to detect the corner, the window size and the zero zone. And the criteria is the iteration time and the precision of sliding windows. You can modify this or use the default setting by the OpenCV. And the second question is find the intrinsic metrics. And here we recommend you to use CP2.calibrate camera. For the input is 3D object point. The 3D object point is the 3D number array. You can see it on the right side. You have to declare this by yourself. And the second input is 2D image point, which is the corner you get from the previous problem. And the second input is WNH, which is the image set. And you can get the four output. The first one is intrinsic matrix. The second one is distortion matrix. And the third one is rotation vector, and the last one is translation vector. In this question, you have to click a button, find intrinsic, and show the intrinsic matrix. This is just an example. Okay, so the below image is the transformation from 3D coordinate to camera coordinate to 2D coordinates. This is just an example. Okay.
The definition.
The definition of the coordinates is like this one. The button, the right button have to be the zero coordinate, the 0 points, and the x is this way, and y is this way, and z is this way. So you have to declare the 3D number as 12 by x by 1. Then you can use it as 3D object poles.
This is image. This image is feedback. So give you the image. The image coordinate. And for this chessboard is the object. Chessboard is the object. So each object has its own coordinate, 3D coordinate. And this one, usually we design this is the 0, 0, 0. So this is the x axis, y, and this one, x, y, and z. So z axis will be inside it. Camera here. The chessboard supports the chessboard. So suppose the chessboard is one chessboard. This chessboard. This is 3D object. Okay. So we define this is x, and this is y. We define by yourself, but I define for you. And x, y, camera is there. So z is there in the other side. Okay. And 3D object has its own coordinate. So that's meaning no matter where it's put, this has its own coordinate. 就3D 的坐标，3D 的物体，它不会随着你到哪边，它自己本身就一个3D 的东西，它不会受什么坐标影响，它本身就一个坐标。3D object has its own coordinate. It doesn't affect by any position. The position is taken by the image by camera coordinate. The camera is fixed, and you put it, the board is here like this one. So this is the image coordinate corresponding to camera coordinate. This is fixed. However, the object move. So object move means you will see object here in the room anywhere. However, if the object itself is 3D object, it has its own coordinate, will not affected by the image coordinate. 这坐标你是要小心一下，这种属于，所以 for 3D, because we will do 3D reconstruction here. So 3D object has its own coordinate. Okay, so that's it.
And for the next question is find the extrinsic matrix. Find the extrinsic matrix on chessboard for each of the 50 images respectively. Okay, so you can get rotation vector and translation vector from the previous problem in.
So 3 extrinsic meaning you have 3D, right? 到前面去，前面上右。哦。因为 camera coordinate camera object here, but object move. So between the 3D camera and the 3D object, between them, there were translation and rotation. That's called extrinsic parameters. 外部参数，所以你在不同 pose 这边都有一个外部参数存在的啊。We will teach you how to calculate, how to calibrate the extrinsic parameters. Okay, so that use that kind of function. So this one, the extrinsic parameters by function call is you already get it. Just the function call is there. So after this function call, okay, this function call, given the 2D image, right? And the 3D is this coordinate. 3D is the object coordinate. 2D is this coordinate. Based on both, and based on each find the corner, and they will do calibration. Calibration result output to you will include camera coordinate. The distortion, this parameter, and rotation translation is this extrinsic parameters. However, the rotation here, the output is the 1 times 3 vector. But my lecture is the rotation matrix is 3 by 3. So we'll teach you how to transfer the 1 by 3 to 3 by 3. The 1 by 3 is meaning there's a vector, so x, y, and z. So that 1 by 3 r, the r rotation is the x axis, y axis, and z axis. We have a function to translate the x, y, z 3 vector to 3 by 3 rotation matrix. They will teach you very soon.
As teacher mentioned before, you can use CV2.Rodriguez, and the input is rotation vector. It will output rotation matrix. So the function is from 1 by 3 to 3 by 3. That one. The RODRIG, that one. Yeah, this one. Okay, and you have to concat the rotation matrix and translation vector to extrinsic matrix. And here we recommend you to use NumPy.H which means horizontal step. It will concat by horizontally, and the extrinsic matrix will like this. If you click the button 1.3, find extrinsic, it will output the extrinsic matrix. Okay. And each of the image has its own extrinsic. So you have to choose the number of the image and show its own extrinsic map. Okay. And the next one is find the distortion matrix. You can get the distortion matrix from the previous function, like 1.2 question. And you click the button on 1.4 find distortion. It will output the distortion, the result of the distortion matrix. Okay. And the final one is show the undistorted result. You can get intrinsic matrix and distortion matrix from the previous problem and use the CV2 dot undistort with input of gray image, intrinsic matrix, and distortion matrix, and you will get the final result image with undistorted. And you click the button on 1.5 show result. It will show the result as this picture. The left side is a distorted image, and the right side is undistorted image. And each image has its own undistorted result. The next this is the demo video. First of all, you have to load the image folder. You click and find corners for the image corners, each picture. One is find intrinsic. The intrinsic matrix will be only one. And the next one is find an extrinsic matrix. Next is find distortion. Show the undistorted image. So here is the question one. If you have any trouble, you can go to the office to ask the student and TA.
I'm here to introduce problem to augmented reality. In this question, we need to load the image provided in our data sets, and they look. Sure. First, load the chessboard image at the load image button, and we should specify the 6 English letters we want to print on the chessboard.
We'll put a chessboard for the AR.
And the first button will show the words printed.
The six characters will show up there.
You should iterate all of the image. And the word on the chessboard vertically standing. And first, I will show and I will introduce the data sets we will provide. The first two are the alphabet database onboard and vertical. These database will contain the 3D word coordinates for all of the alphabets from letter A to Z. And here are the letter K as an example of onboard database. And we can notice that the Z coordinates will be 0 because the letter is lying on the 3D chessboard coordinates shown as the bottom left corner. And as for the vertical database, the y-axis will be 0 because it's standing on the chessboard coordinates on plane, XZ plane.
So this is based on the first question. After we have a first calibration, and the second question is like so this is a chessboard. Suppose this chessboard here, and chessboard because this is a board, so the z equal to 0，就它没有 z， 它没有厚度，就变 z 等于这样子。所以刚刚讲到 z 等于，那刚刚讲是那一个，那另外是这个字，this character each character is an individual coordinate. Each character is an individual coordinate. 这个是这样。
And to use this database, we will use the following two functions. The first one is the OpenCV file storage. We will set up a file storage by inputting the database text file path, and we will specify the mode of the file storage to read. And we can later on use this reader's method get node to get the matrix of the letter K as example, and the character points matrix will be will be this for letter K.
I should explain this one to this one.
Okay.
Japanese.
And for the letter K, we will have three strokes, and each stroke will be is marked as different colors. And the first row is the this vertical line from 220 to 200.
All the characters we give to you is this like this one. So each character has its own coordinate, and in your button side is a 0, 0, 0. 就我们给你每个字都有以这个坐标为主的，所以这个每个字的每个字都有这些点，这些点的坐标表示像 this is K, okay, the K will connect from the button 220 and 200 is that the red one, right? And with blue one is corresponding to that one, and the green one is corresponding to that one. Okay, so each character will give you the point coordinate.
So the output character points matrix size will vary differently between different characters. In letter K, it has 3 lines, so the matrix size is 3 by 2 by 3. If it has 5 lines like E, letter E, 1, 2, 3, 4. 1, 2, 3, 4. Oh, letter E will be 4 lines, so the matrix for letter E will be 3 by 2 by 4. And next, we will introduce the chessboard coordinates. The image provided in the dataset will be the same as question 1. And the definition of the coordinates was the same. And to move the letter along the XY plane, we will, if you want to move the letter to position 1, then we will add 7 to the X value of the coordinates and 5 to Y coordinates to translate it from the original points 0, 0, 0.
Okay. Because this is 3D, the chessboard is 3D. And then this is the position we want to put each character at this position. So each position, this corner corresponding to the bottom corner. Okay. This corner corresponding to the bottom corner. However, each position corresponding to this bottom 0, 0, 0 here. So the position this position correspond to the 0, 0 here. So let's set position. And the other side, the other side, that one, the first one, we define z equal to 0. Z equal to 0 is because this one, this is the x plus x, y. So z equal to 0 it means this character will lie on this board. 就这个字会躺在这个 x y 上面。That's for first one. And then this the board here, and this character will align on the x y plane. So x y plane is fine. The second one we call the vertical. Why we call vertical is because this one, y equal to 0. That means in this plane, y equal to 0. That means each character will be vertical to this ball. The ball will be here, and the ball here. And this each character will be vertical to the ball. So that means each character on this xy plane, xy plane will be here. The y equal to 0 will come to this one. So that means each character will be vertical to this ball. So这样 interface 跟这样。This is the character. This is ball. So we define this one. Z y equal to 0. So this one, each y will be 0. Okay. So this definition is based on this 3D coordinate. Careful about ours. So important. And this is translation. Okay. The 7, 5 is the for example, this. If I want to put this one on this position, I will move 0, 0, 0 to here. That's translation. OK， 所以你每个字要出现在哪边，你要把这个字移到这里来。3D， 在 3D， 这 3D 的东西这样好。注意一下，这是我们在做 AR 的时候这样在做，让
For question one, we want for question one, we want to use the outboard data sets to print the text on the chessboard. The first step was to use the parameters we get from the previous questions using the OpenCV camera calibration function. And the second step, we want to read the characters we put in the UI edit box. In the third step, we want to use the file reader from previous page to get the letters from the text box. And here we also take K as an example. And the outer matrix will be shown as like this on the right side. The fourth step we want to get the we want to project the 3D coordinates onto the image, 2D image. So we will use the OpenCV function project points to project the character points matrix using the parameters we get from camera calibration into our new matrix, new character points. And here is the example of the new character points. We will get the same size of the same size as the character points, but the coordinates will be on the 2D image coordinates. And the last step, we will use the OpenCV line function to draw lines between these points. Take point A and point B from the new character points matrix as example. We will input these two point A and point B. Also, the the original image into the OpenCV line function, then it can draw a line on the between two input points.
就是 if we'll give you this one. For each character, we'll give you this one. That's meaning each pair you draw line to connect together. 就是我们给的时候，那个 library 只有给这些点，但是你要画的时候，你draw between two or one pair. So AB or this one, and then CD, EF something like that. 这样才会看到那个词，不然你会看不到那个词。那个它只有给点的点坐标。
And we will repeat for all the 6 letters, and we will get the results of the prints on board. And for the second one, we just need to change the database to vertical, and the other steps are the same. And here is demo.
就可以用
Here is for question 2.
And I will introduce the question 3. Stereo disparate map. And in the we have introduced above. You need to use the list 2 button. And here is the question. Given a pair of images, INL in PNG format and INR in PNG format, and you need to find the disparate map based on list 2 images. In the first step, you need to load the image left PNG by click this button. And second step, load the right image by this button. And the third step, you need to click the button stereo disparate map to create this result. And here's the hint. You may use OpenCV stereo BN class. And this BN means the block matrix to build a stereo BN object. So you solved. So first of all, you need to create this object by input these 2 parameters. And later I will introduce what is the meaning of these 2 parameters. And here the value is an example. So you can adjust these 2 values by yourself and to create this result you think it's looking better or not. And while you create this object, you also need to use the method stereo.compute and input these 2 images, left image and right image, to create the result disparate map. Then you need to show the disparate map. So you need to normalize the minimum value and the maximum value of the disparate map to interval from 0 to 255. And here I will introduce what is the constraint and what is the meaning of these 2
these two parameters, the number of disparities and the number of block size. The first, the number of disparity, it means the disparity search range. And the constraint, it must be positive and can be divided by 16. And the second, the block size. It means it means the searching window size. And it must be an odd number and within the interval 3 to 51. Okay. And beware, the large block size implies implies the result will be smooth, but it will result less accurate experiment. The small block size, it gives the more detail about the result, but it will increase the noise. So that's all. And also, the input image, the width of the input image is the size of the input image is here. So that's the question. And here is the demo. You need to load the left image. Step 2, you need to load the right image. And click the button. So when we check the homework, you need to demo this, your homework like this one. And if you have any questions about this question, you can go to the laboratory and in the office hour. Thanks.
I'm introducing the fourth question shift. In question 4.1, you should find shift key point of an image. And question 4.2, you should find match key point between two images. And this is the example UI. So first you click the button load image to load this left.jpg. And you click the button key point to show the output with key points. So first you convert the image to grayscale image. And you input the image here and you got grayscale image output. And then based on shift algorithm, you should find key point on left.jpg. So you can call cv2.shift create to create a shift detector. And apply the method detect and compute. And you input the grayscale image, then you got key points and descriptors. And know that there are many shift key points, and it contains coordinate, size, angle, and so on. And each key point has a descriptor. Is 128 dimensional vector. Then you draw the key point of left.jpg. And by calling the function draw key points, and input grade, scale image, and key points. Then let's you show the image here.
Key points. Green one.
Yeah.
Green one is the key points.
And the next question is to find match key points. So you click the button load image 1 and load image 2 to load two images. And you click button match key point to show the output. So based on the safety algorithm, find the key points and descriptors at two images. This is same as question 4.1. Then you find match key points of two images by calling the function bfmetric.knmatch and input two descriptors. And k equals 2. Here means you can find the two closest matched key points for each key point on left.jpg. And m and here mean m is the closest and n is the second closest. So we got two key points, two match key points. Then we apply ratio test to find out the good matrix. It means that if the distance to the closest matrix n is much smaller than the distance to the second closest n, then the match is considered good. And the distance here means the similarity. So you can
show it this way. First of all, you input two images, and then you find the key points on left side will find the key points. Right side will also find the key points. And the third find sure. And for the mesh, actually in this one, it's this in the middle, this is the left and this is right. And each key point, they'll find their corresponding key point based on the descriptor. So this is a line, a long line, that meaning the connection between two corresponding points. And corresponding point is based on the matching. And then so try to find a match point. But there was some constraint. The constraint will be distance, right? Yeah, the distance is this one.
So you can write m that distance is less than 0.75 times n that distance. It will be a good matrix, so you append m into good matrix. Then you can draw the match feature points between two images.
Okay, the match is 0.75 this way, because each point they can find two corresponding points. Okay, because they allow k equal to 2. K equal to 2. That's meaning they can find the best match and second match based on the descriptor. Descriptor is the 128 dimension vector. So I'm sorry, I said 0.75 is like a Euclidean distance. So the similarity between two. Okay, it's not the distance, it's a similarity between two the descriptor. One descriptor is 128 dimension vector. Okay, so that's meaning if this match into 2 points, so one to this one, the other to the other one, and then based on the Euclidean distance. So if this one, the first distance is smaller than 0.75, the second distance, right? That's meaning this point, they correspond to two similarity points, but both similarity points are very different. That's meaning good. So they pick up the first one. Okay, the similarity between this point to first one and this point to second one. And the similarity is different away from the 0.75， 就是它的相似度，它比0.75的相似度还差多的话，那表示 this meaning this best match is good. And the second one doesn't similar. Let's delete it. Okay, but if this point corresponding to point, but both points are very similar, that means this is not a good match. Just delete it. That's meaning if the corresponding point is not unique, that's not good point. It should be unique. So the constraint is 0.75 for the similarity measure.
So let's draw the match feature point between two images by calling the function draw match kn, and you input grayscale image 1 and key point 1 and grayscale image 2 and key point 2 and good matches. Then you got the output, then you show the image here. So here's the demo. You load image 1 and you show key points here. And you load another image and you show match key points. Like this.
This is separate. This is not one image now. That's two images. So it's actually better, it will be separate here. So one image, two image, they find a corresponding point. So actually, for the stitching, you take your cell phone, you put a photo, and you want to do a stitching. Actually, stitching this way. After you find a corresponding point, and you can find the rotation matrix, electricity parameter, and then you can align two together. So that's the stitching. The stitching 是从这里做出来的。So after you find corresponding point, based on the corresponding point, you can find the electricity parameter between two images and can align and then do stitching. So that's when you take the photo like this way, you can stitch the photo together using SIFT, using this method. Okay, so that's for stitching, but I don't do the stitching for you. But let's stitching using the SIFT to do that. Okay, that's the homework for you to do that within 2 weeks. And I encourage you guys to discuss together. But don't copy. Okay, that's for today's lecture.